I've been driving cars for years. I use the pedals to control my speed and the steering wheel to control turning. To fly an airplane, I just need one more control so I can control altitude. Is that right?
Well, there is more to it than that. For one thing, there is an intermediate thing called airplane attitude. We use the aerodynamic controls to change the airplane attitude. Then, the airplane attitude in combination with the power setting determines what the airplane does.
Oh, I can see how that would make it a little more complicated than driving a car. Another issue is that some of the controls have secondary effects. In other words, they change something other than the intended effect of the control. The pilot needs to anticipate those effects and use other controls to counteract the secondary effects. This is starting to seem complicated.
The primary effects of each control are mostly consistent in different phases of flight and even in different airplanes. The secondary effects vary from one phase of flight to another. Some secondary effects are much more noticeable in certain types of airplanes.
Whoa, that seems really complicated. How does anyone ever learn to fly?
Don't worry. In each phase of flight, there are control rules for how to make the airplane do what you want. Normal people learn to fly every day, but it does require training.
One of the first things you'll learn when you start flight instruction is how to manipulate the primary flight controls when you're in the air. Most instructors will initially teach this at moderate speeds, and then later on they'll teach you how the flight controls behave a little differently at low speeds or high speeds. I take a somewhat different approach to explaining this. I develop an overall theory for how the flight controls work, and then I treat separate phases of flight or particular maneuvers as special cases of that general theory. I'll start by discussing the effect of each of the airplane's primary aerodynamic controls on the aircraft attitude. Then I'll describe how the attitude and power impact aircraft behavior. Of course, our goal is to work in the other direction. We start with an idea of what we want the airplane to do, and then we need to figure out what control inputs will accomplish that. In each phase of flight, there are control rules for using the primary flight controls. This airplane looks like it has a bad attitude today, but the term airplane attitude does not refer to whether the airplane is being belligerent or grumpy. Airplane attitude refers to the orientation of the airplane. Specifically, airplane attitude refers to the orientation with respect to three different axes. Pitch attitude refers to the nose up or nose down attitude relative to the horizon. Roll attitude refers to the wing angle relative to the horizon. And finally, yaw attitude refers to the movement of the nose left or right relative to the direction that the airplane is moving with respect to the air. We'll start by talking about the ailerons. The ailerons are control surfaces on the trailing edges of the wings, usually located toward the wingtips. The pilot moves the ailerons by rotating the yoke or by moving the control stick left or right. One aileron moves up as the other aileron moves down. Downward deflection increases the lift and the drag on that wing. Upward deflection decreases the lift and the drag on the other wing. The increase in lift on one wing causes the airplane to roll. The change in roll attitude caused by that asymmetric lift is the main effect of moving the ailerons. The asymmetric drag causes a secondary effect on yaw called adverse yaw. It's called adverse yaw because it's in the wrong direction compared to the direction we want the airplane to be yawing when we turn the ailerons. Adverse yaw is strongest for aircraft that have long wings, such as gliders. There are things that designers can do to reduce the effect of adverse yaw. and many modern trainers have a lot of the adverse yaw engineered out of them. Therefore, a lot of pilots don't really fully appreciate how strong adverse yaw can be until they fly an airplane that was designed in the 1940s or 1950s. Now let's move on to the elevator. The elevator is a control surface on the trailing edge of the horizontal stabilizer. This is deflected upwards by pulling back on the yoke or the stick. Doing that makes the tail go down and the nose go up. Pushing forward on the yoke or the stick has the opposite effect. Therefore, the primary effect of the elevator is to change the pitch attitude. There's also a secondary effect of using the elevator due to a phenomenon called gyroscopic precession. The spinning propeller acts as a gyroscope. When we change the axis of rotation of a gyroscope, there's a reaction torque that is offset by 90 degrees. This creates a yaw moment in response to a change in the pitch attitude. This secondary effect of yaw is strongest in airplanes that have a large propeller, and it's strongest when that propeller is turning at a high speed. The final aerodynamic control is the rudder. The rudder is a control surface on the trailing edge of the vertical stabilizer. The pilot moves the rudder by pressing on the pedals. The primary effect of the rudder is to change the yaw attitude. As the airplane yaws, one wing will be moving faster than the other wing. This causes a secondary effect because as one wing moves faster, that wing will have more lift. That creates a rolling moment. Also, gyroscopic precession works in response to rudder deflection also and causes a pitch change. Since each of the controls has secondary effects, it's necessary to use multiple controls when you want to change only one axis of the airplane attitude. For example, when you want to roll into a bank, you use the ailerons for their primary effect, and then you use the rudder to counteract the adverse yaw. Whenever a secondary effect is strong, it's important for the pilot to anticipate that effect and apply the other control at the same time as the primary control. For weaker secondary effects, it's okay for the pilot to wait until the effect is observed and then react to that effect. Now that we've discussed how to change the airplane attitude, we need to discuss how the airplane attitude impacts airplane behavior. There are three aspects of airplane behavior that we want to control: airspeed, rate of turn, and rate of climb. We'll start with the effect of pitch attitude. If you start in level flight above stall speed and you increase the pitch attitude, the airplane will initially start to climb and then it will start to slow down. As it slows down, the rate of climb drops off. Eventually, the airplane reaches a new steady state speed that's less than the original airspeed. In that new steady state condition, the airplane may still be climbing or it may be descending. That depends on the airspeed. In other words, pitch has a transient effect on rate of climb that's positive. But the lasting effect is positive at cruise speed and negative at low airspeed. I'm labeling the effect on climb rate a secondary effect because it only occurs in some flight conditions. Some people would object to calling this a secondary effect because it is strong in cruise flight. When an airplane is in a nose-up pitch attitude, the downward moving propeller blade encounters the air at a higher angle than the upward moving propeller blade. This causes more thrust on the right side than on the left side. This causes a secondary effect of pitch on yaw called P-factor. P-factor is strongest when you're operating at high power settings such as during climb. Therefore, you often need to hold right rudder to counteract this effect during a climb. Now let's consider the effect of roll attitude. When an aircraft banks, the wing lift vector has a vertical component and a horizontal component. The horizontal component causes the aircraft to change direction of motion, or in other words, it causes it to turn. If the magnitude of the lift vector stayed the same, the vertical component would not be sufficient to counteract weight anymore. Therefore, unless other controls are used, the aircraft will start to descend. Therefore, roll attitude has a secondary effect on the rate of climb. Now let's consider the effects of yaw attitude. In most flight conditions, we want the airplane to be pointed in the same direction that it's moving through the air. When the airplane is misaligned with the airflow, a sideways force causes the airplane to turn, and the increased drag causes the airplane to descend. There are some circumstances, such as when you want to lose altitude, where the effects of pointing the airplane in a different direction than it's moving are desirable effects. The last primary control is the power control, generally the throttle. When you increase the power setting with the airplane in a constant attitude, the airplane will speed up. That increase in speed increases the lift, which causes the airplane to start climbing. Soon you'll reach a new steady state condition where there will be a slight increase in speed and a significant increase in climb rate. I've labeled the effect of climb rate as the primary effect and the change in airspeed as the secondary effect. There are other secondary effects to changes in the power setting. The first of these is caused by the propeller making the air rotate around the airplane as it flows past the airplane. The air hits the vertical stabilizer on the left side. That causes a left yawing tendency called the slipstream effect. Secondly, the engine must apply torque to the propeller. There's a reaction torque on the airplane that causes a roll effect called the torque effect. And finally, in some airplanes, such as a seaplane where the engine's mounted above the wing, the thrust line is offset a long ways from the center of gravity. In that case, there's an effect on the pitch attitude whenever you change the power setting. This diagram puts together the material from the previous discussion. As you can see, controlling an airplane is a lot more complicated than just three-dimensional driving. Fortunately, many of these secondary effects are small in most phases of flight, so you don't need to anticipate them and counteract them all of the time. Also, many of these secondary effects are small in particular aircraft. This illustrates why it's important to get a good checkout when you first fly an airplane that's different from the airplane you're used to. The new airplane may have some strong secondary effects that you were able to ignore in your previous aircraft.
When I look at that drawing, it looks like I could just use the elevator to control airspeed and use the ailerons to control rate of turn. Why do I need to worry about airplane attitude?
When you move the elevator, it takes some time for the pitch attitude to change. Then it takes some more time for the airspeed to start changing. This delay between your action and its effect causes you to over-control. It works much better to decide how much you should change the pitch attitude and move the elevators accordingly. Then, after the airspeed has stabilized, make another correction if necessary.
Okay, but that diagram seems way too complicated. There must be a way to break it down so I don't have to think about all of that at once.
The best way to break it down is to think about different phases of flight or maneuvers one at a time. The control rules in each phase of flight are manageable.
Now let's consider different phases of flight one at a time. Let's start with cruise flight. The objective during cruise flight is to stay on a selected heading and to stay at a selected altitude. That may be a heading and an altitude that we chose ourselves or one that air traffic control assigned to us. We'll use a power setting that's a compromise between cruise speed and fuel usage. So higher power settings will give us a better cruise speed, but we'll use more fuel to get where we're going. On our way, we'll encounter some updrafts and some downdrafts. We may have unintentional pressures on the controls that cause us to change altitude or change heading. So we're going to react to those deviations in altitude by temporarily adjusting the pitch attitude. We're going to accept the fact that the airspeed might change for a little while we're making our altitude correction. We're going to react to heading deviations or heading changes by making shallow turns, which will be discussed on the next slide. Now let's consider level turns. The objective during a level turn is to change to a different heading without changing our altitude. The first step is to choose a target bank angle. For small heading changes, we will typically choose a very shallow bank angle, like 10 degrees. If we need to make a larger heading change, we'll choose a steeper bank angle so that the heading change doesn't take as long to take effect. Then we'll use the aileron and the rudder together to establish that target bank angle. We'll add some nose-up pitch or some power while we're doing that in order to avoid losing altitude. The amount of rudder that you need is determined by keeping the ball centered. With practice, you get good at judging the amount that you'll need in advance. Once you've established the bank angle, you'll need less aileron and rudder to maintain that bank angle. In fact, quite often, you'll need reverse direction aileron in order to maintain that bank angle because of a tendency called the overbanking tendency. If you're trying to do a target turn rate, such as a 2-minute turn, then you'll make adjustments to that target bank angle if you're turning either too fast or too slow. If you're turning faster than the 2-minute turn, then you'll choose a shallower bank angle. If you're turning too slowly, you'll steepen the bank. As you approach the desired new heading, you'll use the aileron and the rudder together to level the wings, and you'll remove any elevator pressure or power that you added when you rolled into the turn. A steep turn is used when you want to change heading rapidly. Any turn with a target bank angle over 45 degrees is considered a steep turn. The main difference you'll notice between a steep turn and a shallow turn is that it requires a lot more back pressure in order for you to maintain altitude during a steep turn. And during the turn, you'll notice a lot more G-forces on your body. During a steep turn, you'll notice that the elevator is more vertical than it is horizontal, and the rudder is actually more horizontal than it is vertical. The result of this is that the elevator is not very effective at changing your pitch attitude. When you pull back on the elevator, it does more to tighten your turn than what it does to actually raise the nose. There's two ways to deal with it if you are losing altitude during a steep turn. The first thing you can do is you can temporarily roll into a shallower bank and then hold more back pressure as you roll back into that steep bank. The other thing you can do is use a little bit of top rudder during the steep turn to raise your nose. Different instructors will have different preferences between these two methods, so you should talk to your instructor and make sure you are doing it the way that your instructor prefers that it be done. Now let's consider the phase of flight where you're climbing or increasing your altitude. So the objective when climbing is to gain altitude while continuing to make progress toward your destination. You'll use full power for climbs, and you'll select a target airspeed that's a compromise between the climb rate and progress towards your destination. So right after takeoff, in your initial climb, you'll choose a speed based on the best angle of a climb or the best rate of climb airspeed. Those are published numbers for your airplane. Once you're established on course and pointed in the right direction towards your destination, then it's common to choose a faster target airspeed, which will reduce your rate of climb somewhat, but decrease the amount of time it'll take you to get to your destination. You use pitch attitude to maintain that target airspeed. During the climb, the P factor secondary effect is very strong, so you'll need right rudder to avoid constantly yawing off to the left. If you need to make turns while climbing, they are accomplished essentially the same way as level turns, except that you're trying to maintain your target airspeed during the turn as opposed to trying to maintain a target altitude. We use a descent to get from our cruising altitude to traffic pattern altitude, or to change from one cruising altitude to a lower cruising altitude. Descending within the traffic pattern will be discussed on the next slide. The target airspeed during a descent is typically close to the cruise airspeed because we're still trying to make it to the destination and we're still trying to make good time. The target descent rate is calculated whatever you need to in order to get to the traffic pattern altitude before you get to the traffic pattern. Preferably, we'll plan ahead and we'll start the descent at an appropriate time so that a descent rate less than 500 feet per minute gets us there. Sometimes things happen and that isn't possible. The power setting we'll use during descent is going to be a few hundred RPM less than the cruise power setting. We'll know from experience based on that aircraft how much to reduce power in order to get a target descent rate. When you're descending, you may notice variations in what you're actually getting for a descent rate based from what you were targeting, and you'll make an adjustment for that. That adjustment can be either by using power or by using pitch. Since we're close to cruise airspeed, either one will work. Whichever one you use, if you notice that your airspeed is varying very far from your target, then you'll use the other one to make that adjustment. Now let's consider flight in the traffic pattern. In the traffic pattern, our target airspeed is going to be based on our landing speed. It might be a little bit higher than our target landing speed, but not very much higher because we don't want to be making big speed changes while flying in the traffic pattern. We use power to control our descent rate. At these airspeeds, pitch has very little effect on climb rate or descent rate. It'll have a transient effect, but very little lasting effect. So we need to use power as our tool to control descent rate. When we're on final approach, we'll be more concerned with the descent angle rather than the descent rate, but we'll still be using power to make our adjustments. We'll be using pitch to control the airspeed. We'll need to make turns during the traffic pattern. Turns are done the same way in the traffic pattern as they're done in other places by establishing a bank angle, holding it until you get to the desired heading. We want to plan the size of our traffic pattern such that we only need shallow turns. The last phase of flight we'll consider is slow flight. The objective during slow flight is to maintain an airspeed that is just barely above stall speed without changing your altitude. You may wonder, why would you ever need to do that during a normal flight? The answer will be clear when we start talking about short field landings, because in short field landings you won't fly quite that slow, but you will fly almost that slow. And it's important that you be comfortable controlling the airplane over a wide range of airspeeds, wider than the airspeeds that you will actually need to use during real situations. In slow flight, you use pitch to control airspeed. Nose up pitch will cause a loss of altitude. When you raise that nose, you might get a very momentary climb, but it lasts a short amount of time and pretty soon you'll be descending if you have the power the same. So pitch is very ineffective way to control your airspeed or control your altitude. You will use power to control your altitude. You may be surprised at how much power you need to use to control your altitude. It tends to take much bigger power changes than you were using in other phases of flight. When you make a turn in slow flight, you need to choose very shallow bank angles because any increase in bank angle puts you closer to your stall speed. You'll notice that the ailerons feel really mushy and that even to make those shallow turns you might need to use quite a bit of aileron deflection. Rudder continues to be effective, much more so than what ailerons do. And even when you're making these really shallow turns, you'll notice that it requires a big change in power in order to maintain altitude. And you have to do it with power. If you try to adjust for that altitude with pitch, it won't work.
Wow. Controlling an airplane is more complicated than I thought it would be. But if we focus on one phase of flight at a time, it is something I think I will be able to master with some practice. First, I need to decide what airplane attitude and power setting will make the airplane do what I want. Then I need to use the elevator, ailerons, and rudder to put the airplane into that attitude.
That's right. As you progress to more powerful airplanes or airplanes that have different configurations, some secondary effects might be different than the airplane you learned in. So it is important to get checked out by a flight instructor when you fly different airplanes.